Hello, this is Brother Cromar from the Maths Department at BYU, Idaho, and these next videos I'll be covering Lesson 18, dealing with inference for one proportion. And here's the outline for these videos. First, I'll be covering confidence intervals, followed up by hypothesis testing. Now I'll be mentioning descriptive statistics and checking requirements throughout these two sections. Okay, so let's review parameter and a statistic. So a parameter is a measure of the population that's typically unknown, but we like to estimate. And so what we saw back in Unit 2 primarily was population mean, which is mu. Now we're going to deal with P, which is a population proportion. And a statistic is a measure from the sample, and the statistic is used to measure the unknown parameters. So X bar was used back in Unit 2, which is our sample mean, and our sample mean is used to estimate our population mean. And now P hat, which is our sample proportion, P hat is used to estimate P, which is a population proportion. Okay? So now, distribution of a sample proportion. So sampling distributions have many sample proportions for many samples. However, due to time and many, one cannot take multiple samples or sample the whole population, so we infer based on one sample. So a statistic from a sample can be anywhere in the sampling distribution. So say, for instance, we get a sample proportion. It can be anywhere. If you look down below here, it'll be anywhere within this curve. Okay. Going back to lesson 17, as you recall, if we have a large enough sample size, we can assume that this distribution of all possible sample proportions is normal. Okay. So now let's go to confidence intervals. So a confidence interval for an unknown parameter consists of an interval of numbers. So this is review. And so a confidence interval basically involves a point estimate plus or minus a margin of error. For instance, in a pre-election poll before a general election, say for instance we're interested in seeing how many people will vote for President Obama for re-election. And say for instance in our sample we get 48% that say will vote for President Obama, but we have a plus or minus 4%. So this would be our confidence interval where we take the 44% plus or minus 48% plus or minus 4%. So we would be X% confident that the percentage of people voting for Obama would be between 44 and 52%. Okay. So now this goes to our confidence interval. How do we construct our confidence interval? Now in the book it talks about using what's called a +4 confidence interval, and based on results that we're seeing historically, as you read in the online textbook, you will see that this is a more accurate confidence interval to construct versus the traditional confidence interval doing with one proportion. But basically, here's the formula for it, and P tilde is basically x plus 2 divided by n plus 4. X represents the number of successes. For instance, if we took a sample of 1,000 people to see how many people would vote for Obama, and we found out that 480 would, so 480 would be x, and then 1,000 would be n. Okay, and if we put those numbers into the formula, we would get P tilde. Z critical value you've seen before because this is dealing with a Z distribution, and is our sample size, and everything to the right of the plus or minus sign is the margin of error. Okay, so then the next slide is an example. So let's go through an example. I'll go through this one by one. So before the election, you conduct a survey of Californians to see if they are in favor of Proposition 8. You take a simple random sample of 1,000 Californians, and out of your sample, 540 in your sample say that they are in favor of the ballot measure. You would like to get a 95% confidence interval of those who are in favor of the proposition. So step one is get a sample proportion, or the adjusted sample proportion, using the +4 estimate. So what we do is in this case is that we take x plus 2, and x would be 540 because 540 represents the number of people that are in favor of Prop 8, divided by our n plus 4, and n would be our sample size, which is 1,000. And so if we put those numbers together, we would have 542 divided by 1,004, and that's equal to 0.540. Next step, and I'm jumping the gun a little bit, is to check requirements. Now the requirement is met if our sample size is greater than or equal to 5. But since our sample size is well beyond 5, we can assume that the requirement is met. And I'll mention that a little bit later in the next slide. Okay. Then lastly, construct and interpret a 95% confidence interval for the true proportion of those who are in favor of the proposition. So here's the formula for it. And so if we plug it in by hand, we would get 0.54 plus or minus, and then we put in the critical value, which is 1.96 for the 95% confidence interval, times, and then the square root, we take P tilde times 1 minus P tilde divided by n plus 4. And if we solve for that, we get 0.509 for our lower bound and 0.571 for our upper bound. So we say that we're 95% confident that the true proportion of Californians in favor of Proposition 8 is between 0.509 and 0.571. Now, as a review, what happens to the confidence interval as the level of confidence in the sample sizes change? Okay, so as the level of confidence increases, the width of our confidence interval, or the width of our margin of error, also increases. But as our sample size increases, the width of our confidence interval, or the width of our margin of error, but it decreases. Okay. Now, what we're going to do is I'm going to take this example, and whether you're in Math 221, 222, or 223, you're going to be using this if you'd like. And so what I'm going to do is I'm going to put in our data, 540 is x, 1000 is n. So if you go to this is a tool that you can use if you want to use it for Excel, and your teachers can show you where to get it. So you put in 540 for x and 1000 for n. And so when you solve for that, you would get down below here as your confidence interval. Okay, this is pretty nice. And if you want to set your level of confidence here, you type it in decimal form. Okay, so now let's go through another example. So a sample case of a sample of cases from the Superior Courts of Massachusetts was used to investigate the outcome for first-degree murder trials. The sample included 57 subjects who were on trial for first-degree murder. Out of these, 9 of the defendants were found not guilty, constructed and interpreted a 95% confidence interval. If you want to stop the video and see if you could do this yourself, that would be great. So here is, first of all, get the estimated or adjusted sample proportion, or p-tilde, for those in favor. So we would take x, which is, so 9 would be x, and 57 would be n. And so we would get, for this problem, we would get 11 divided by 61, which would be 0.180. Then we would check the requirements, and since 57 is greater than or equal to, is greater than 5, we can assume the requirement is met. And then do the confidence interval. Construct and interpret a 95% confidence interval for the true proportion of those who are found not guilty. And so this is our formula. And so if we put that, if we did this by hand, this is how you would calculate it. And so we would say that we are 95% confident that the true proportion of subjects are found not guilty of first-degree murder is 0.084 and 0.277. Okay, or I should say is between 0.084 and 0.277. Okay, so now if we were to use this in our tool here, I would put in 9 for x and 57 for n, and then this is where we would get our confidence interval. Okay, so now a couple more things before I conclude part 1. So for the sample size calculation, sample size is required to estimate the population proportion with the level of confidence of 1 minus alpha times 100%, with a specified margin of error m is given by, and so here's there's 2 different formulas. We use the first formula if we have a prior estimate of p. But if and then we would stick in that prior estimate of p under p star or p asterisk. But if we don't have one, so we're going to be more conservative, we're going to use this formula instead. So for instance, if we have a desired margin of error of 3% with a 95% confidence interval for the Proposition 8 problem that we covered earlier, and if we had a prior estimate of 60%, okay, what we would do is that we would put in, so we use this formula up here, and so we would put in 1.96 because we're interested in 95% confidence interval, divided by our desired margin of error, which is 0.03, and then we times it, and we square that, we times it by our prior estimate, which is 0.6, times 1 minus 0.6, and if we solve for that, we get a number of 1024.43, but we always round up, and so the desired sample size would be 1025. Okay. Now, if we did this again where we had no prior estimate of p, then the formula is shorter, but we have to put a 2 in the denominator here within the squared function here. And so if we solve for that, then we get a slightly higher sample size, or number of 1067.11, but if we round up, we get 1068. So if you want to stop the video and try one more example, actually, well, I have the example up here, so let's just go through it anyways. Desired margin of error of 3% with a 95% confidence interval for a sample of cases from the Superior Court of Massachusetts with a prior estimate is 0.82. So if we want to get a sample size, what we would do is that we would take 1.96, since we're doing a 95% confidence interval, divided by our desired margin of error 3%, square that, and then times it by our prior estimate of p, which is 0.82 times 1 minus that, and we would get 630.02, and then we would round that up to 631. And so that concludes part 1 of lesson 18. So I'll continue with confidence intervals and get into hypothesis testing for part 2.